Okay, so it's, thermodynamics, right? This notion here is that if we've got a gas, a working gas, right, in a cylinder, okay, if heat flows in, right, then there's one possibility is that the internal energy, the internal energy increases, and you can calculate that with this, right? Okay, it can increase, or we can do work, which is, of course, we can calculate that with this, right? So if heat flows in, we can push the piston out, or we can have the temperature rise, or we can have some combination thereof, right? This is basically conservation of energy. So if you give me 10 joules, I could store 2 of it as internal energy and have 8 joules of work, and we can just mess with that, right? So this is conservation of energy, really is what it is. Okay, this is the total internal energy of an ideal gas, of a monatomic ideal gas. This 1/2 comes from 1/2 mv squared, and the 3 comes from actually the 3 dimensions, x, y, and z, that the particle is free to move in. Be careful if it's a diatomic gas, you know, it gets dodgy, right? We also discovered, by the way, that the change in internal energy for isobaric. So isobaric is if we have a PV diagram, right? Isobaric's like that, right? The pressure stays constant, right? The U is the change in U is equal to 3/2 P delta V, right? So this evidently, they just put that in the mark scheme like, okay, of course, for an isobaric process, so one that's level like that, you can just say that, right? This is entropy. So this is, of course, kelvins of temperature, right? That's heat flow. So that's joules. So really, entropy is in joules per Kelvin, right? And that's entropy. And that's going to be joules per Kelvin. Okay. This is for an adiabatic process, right? P times V to the 5/3 is constant. Because if it's isothermal, PV is constant, right? Right? Because PV equals nRT. If it's constant temperature, T doesn't change, R doesn't change, moles doesn't change, right? Okay, so this is for isothermal, same temperature, right? So if the temperature doesn't change, PV is constant, right? If it's adiabatic, that is when you compress it, the temperature rises, then this is true. Okay, PV to the 5/3 equals PV to the 5/3. Okay, this is just a general statement of efficiency. Okay. And then this is the Carnot cycle. It's the ideal, right? Basically, nothing can be more efficient than this. These are, of course, kelvins. This is the cold temperature of the temperature of the cold reservoir, temperature of the hot reservoir, and then this is the efficiency. Remember that it cannot be more efficient than this. Okay. I think that's all I have to say about that.